The formation of hydrogen bonding. Before the discussion of hydrogen bonding, there is a term called electronegativity. And according to definition, electronegativity is the tendency of a species to attract bonding electron towards itself in a covalent bond. And the most electronegative species are F, O, and N. And the formation of hydrogen bonding actually happens here. Say for example, when F, it bonds with hydrogen, originally if they attract bonding electron to the same extent, you can imagine that the bond pair electron are located right at the middle between H and F. However, is the case? The answer is no. F, being the most electronegative species, is drawn the bonding electron toward itself. So that for hydrogen, it will bear a positive, very positive end, and then for F, it bear a very negative end. And for hydrogen, because it has only one shell with only one electron inside, after this shifting of electron density, hydrogen will just look like a really bare proton, which is very highly positive. And for F, with the existence of some lone pair on it and it drawn the electron density from hydrogen, it will become a very negative end. And if there are two HF molecules, the very negative end lone pair on F will attract the very positively paired proton on another HF. And this electrostatic attraction is called hydrogen bonding, which is a relatively quite strong intermolecular attraction. The evidence of hydrogen bonding, we can actually use the boiling point among group 5, group 6, and group 7 member after the compound with hydrogen and look at the boiling point of the compound formed. And here I use group 6 elements as an example: H2O, H2S, H2Se, and H2Te. And as you may see, for H2O, the first member, it has an exceptionally high boiling point. And then it will drop to H2S, and then it will gradually increase. And this shows an inverted trend of boiling point. And what's wrong with this H2O? There is hydrogen bonding between molecules because O is quite electronegative species and it draws electron density from hydrogen. And then for hydrogen, it just looks like a bare proton, which is highly positive. I mean, between these two water molecules, there will be strong hydrogen bonding. However, for H2S, H2Se, H2Te, there is a lacking of a very electronegative species, and they cannot form hydrogen bonding. And they are simple molecular structures, so that there are van der Waals forces, which is a weak attraction between molecules, so that their boiling point are relatively lower than that of H2O. However, can you explain why is there an increasing trend? Oh yes, it's just because the increasing surface area, increasing number of electrons, and it gives rise to increasing chance of instantaneous dipole-induced dipole attraction. There is an increase in van der Waals forces, so that there is an increasing trend of boiling point. However, for this boiling point, they are still lower than that of H2O. The comparison of boiling point among H2O and NH3. As you may know, NH3 is a gas undergoing turbulent pressure, and water, of course, water is a liquid. It means that the intermolecular attraction of H2O should be stronger than that in NH3, and here is the reason why. For hydrogen bonding formation, there are two criteria. First is hydrogen bond with a very electronegative group, and here O and N. And the second criterion is that there should be lone pairs on some electronegative species, say for example NOF. And here O has lone pair and N has lone pair here. And look deeply into the study is that when we consider one mole of these two types of molecules, For NH3 in 1 mole, there's 1 mole of lone pair N, and there are 3 NH, 3 hydrogen bonds with N. If you want hydrogen bonding to form, you must meet the 2 criteria. And now, because there is only 1 pair of lone pair on N, so that it becomes the limiting factor for the formation of hydrogen bonding, so that in 1 mole of NH3, only 1 mole of hydrogen bonding can be formed. However, it is not the case in H2O. It's because in 1 mole of it, we have 2 moles of OH bond and 2 moles of lone pair. Nothing is in excess or limiting, so that 2 moles of hydrogen bonding can be formed per mole of H2O. So given that if there is same mole of H2O and NH3, of course more hydrogen bonding needs to be broken down. More heat is emitted, so the water should have a higher boiling point. For 2 more applications for hydrogen bonding instead, this one we can account for the solubility on whether 2 liquids are miscible. So for example here is ethanol, CH3CH2OH, that is the commonly used alcohol, and here is H2O, water. And as you may know, the alcohol, they are soluble, they are miscible in water. Why? It's because hydrogen bonding can be formed between these 2 molecules. This lone pair can be attracted by this very positive proton on hydrogen, and then this hydrogen can be attracted by this very negative lone pair on H2O, so that the energy required to break down the solvent attraction and solid attraction can be compensated by the hydrogen bonding formed between these H2O and alcohol molecules, so that they are miscible. And this is the first application. And the second one is that we can account for the viscosity or boiling point of some species with different number of moles of hydrogen bonding per mole of molecule. And I use these 3 as an example. In both of these 3 things, they are a chain with 3 carbon atoms. However, for the first one, it has only 1 OH, and this one 2 OH, and then 3 OH. And for the first one, for 1 mole of it, they can only form 1 mole of hydrogen bonding, and then at the middle, there are 2 moles of hydrogen bonding, and then for the final one, you can form 3 moles of hydrogen bonding per mole of molecule. Of course, this one, glycerol, has the highest viscosity because the number of moles of hydrogen bonding per mole of molecule is higher. It means that more energy is emitted, more force is needed to separate these molecules.